Since it's 11 a.m. already, I think we should start with the with today's live session. Am I audible? Sahil, Sufyan?
Yes, you are clearly.
Okay. Good evening, everyone. My name is Vishal. I, along with Sufyan and Sahil, are the team developers of AB, the in e-Yantra's robotic competition. Today's live session is a guest lecture from two speakers, which are Mr. Banerjee and Mr. Yasuhiro. Today's live session will be covering the topic computation algorithms and their real-life application. So with Banerjee covering the part of different of various machine vision algorithms. Professor Biplab Banerjee is Professor at IIT Bombay at CSRE department. Right? Mr. Yasuhiro is the CTO and director of AW Japan. I wholeheartedly welcome the speakers. Professor Biplab Banerjee, sir, I think you can start with your presentation.
Yeah, sure. There's some echo. Okay, just a minute.
Is the echo still there, sir?
I think it's fine. Yeah, sure. That's okay. Should we start?
Yes, sir, please.
Okay, fine. I hope it's full screen now, right?
Yes, sir, it's the entire screen visible.
Okay. So, a very good morning and thank you, eYRC, for organizing this session. So what I'll do for the first approximately 20 to 30 minutes, I'll take you to some problems in computer vision and visual inference, and mostly I'll talk about the problems and how the recent learning techniques, particularly the deep learning, they come into the picture. Okay. So, first of all, thanks to several online resources and blogs, which helped in making the slide, of course. Fine. So, as we know that computer vision is the study of the visual data surrounding us. It could be in the form of images or it could be dynamic videos. Right. So, and given a scene, for example, computer vision, or rather, we can say high-level computer vision, they try to answer different questions. Some of the questions could be given the scene, just to let us know what kind of scene this is. Is it an outdoor or an indoor scene, right? Or just to localize the cars in the scene, okay? Or just to find out, given a reference frame, how far is the building from the frame, right? Which is basically the depth estimation problem. Now, why computer vision matters so much nowadays? Because of their applications in different domains, be it safety, medical, diagnostic, security, or in entertainment industry, biometric. In many places, they are like nice applications. Now, like if we just look into the history of it, the traditional computer vision research started around 1960-66. During that time, when Minsky, a student, he took a project, a summer project in computer vision area. Now, after that, people started dealing with visual data, and people started with the problem of object recognition, for example, the geometric shapes. Then gradually improvements in the area of image processing started coming. Edge detection, interest point detection, tracking those problems become quite popular. And subsequently, the neural network came into existence, which could be implemented on a digital computer. And after that, several applications they start pouring into, right? So be it face recognition using eigenface, object recognition, then the video processing starts, So this is basically a very, very brief pathway of how the computer vision algorithms actually evolved over time. Now, nowadays, like if you see some of the applications, for example, here, like we have this number and we need to recognize the individual digits, right? So it could be the recognition of the card plate, or it could be like from the postal code, we recognize the address. Okay, so this could be some challenging applications. Or like when we click something on the camera, like automatically the face portion are detected, right? And this is agnostic to any type of scene or the number of people in the scene. Okay. Or like we can have cameras nowadays where the shutter clicks when somebody smiles in front of the camera. Okay, so this is basically detecting this particular phenomena, and based on that, something is happening, right? In this case, the shutter flows. Okay, so or like basically we know that images are 2D, they are projected on the 2D plane. But this is a projection from the 3D real world to the 2D plane, right? So how can we get back the third dimension, basically the depth dimension from these 2D images, right? So there are much development in this area as well. There is stereo vision, there is multi-view geometry, which takes multiple images of the same scene but taken from different viewpoints, and they aggregate the information, they find the disparity, and that subsequently helps in finding the depth information, right? And nowadays there are different representation of this 3D quantity. It could be volumetric data, or it could be point cloud data, or it could be simple mesh. So these are the ways by which we represent the data. So when we talk about simple image, we know that we represent as a 2D grid. It has certain number of rows, certain number of columns, and if it is a color image, so there are 3 channels. On the other hand, this type of representation, as you can see, so they cannot be put into using this coordinate system. So here, like we need a completely different kind of representation, right? It could be a graph, it could be a simple point cloud where the point is defined to be some XY lat long, and the depth with respect to some reference. Okay, so and this is also some visual data. I would say, and they also have several applications. So now the point cloud based deep learning, or voxels based methods, so they are quite popular. Now, then of course, the major chunk of this research goes into the object recognition problem. And this basically means that given a scene where a couple of objects may be present, we need to identify their class, right? And this problem may come up in multiple scenarios, like recognizing birds, recognizing cars in a road, or recognizing, for example, the products in a supermarket. Recognizing the human in a biometric unit, and the range of the problems under object recognition is really huge. So, and of course, from the learning point of view, this problem could be very complex, because in some case we may have enough supervised training data available from which we can do the learning, but on other cases we may have very little amount of data, right? Because making this training data is really costly and resource intensive. So that's why, like, the goal of research nowadays, how to make good recognition system of which are trained from very few training data. Okay, so then of course, like the problem you can see the iris recognition, because the other problem is the scene may change. On the scene that we had during training, or the scene that we will encounter during testing. So that may change drastically, right? So how can we make the system adapt to this changing environment? Okay. Now, object recognition I already mentioned, and so now Tsuchida-san will talk more about it. So how to implement these algorithms, on a handheld device, okay? Because here and the memory is less, computing is less, So in this constraint scenario, how can we make these algorithms work? Fine, and of course, like I mean, if we talk about graphics and rendering, so there are much work have been done in the field of shape capture, finding a 3D model for a given object, this kind of stuff. And nowadays with self-driving cars, all the problems that I mentioned before, be it depth estimation or classification, detection, all come handy in this case, okay, in driverless car. So they have to find who are, I mean, in front of the car if there's a chance of accident or just to maintain a gap with another car, So these cars are basically mounted with cameras in all the four direction, and they do this vision applications simultaneously. Okay, so one of this application is Google Card, and as you can see, the camera mounted on the top. Fine. And of course, like if you are used to gaming, then you might have heard about Kinect. So here, so it has a depth sensor. So and it can do this activity recognition. So whatever you are doing in front of the camera, it can imitate that, and that is transferred to the character in the game. So these are like some of the applications that that are there on our day-to-day basis. Uh, Vision have been applied to other kind of data as well. For example, on satellite data, or I mean, when there's a Mars mission or Moon mission, so they take photos of those surface and then they do the analysis, right? And here they have kind of interesting problems. So how to ensure that the landing is safe, so it's not in some crater or anything. So how to combine images to get a bigger field of view, which is called the panorama stitching. So when the rover moves in the moon surface or Mars surface, how to ensure that there is no obstacle. So if there's obstacle, it should bypass that. It should track the movement of the rover. So these kind of problems come when we talk about vision in space, right? Fine. And of course, nowadays in robotics, there are much application because robot navigation and all, it requires computer vision. Okay. For example, when I mean, of course, in this Mars, or if you have a robot which can clean the dish, or I mean, there are some applications which I was showing the other day, like the robot can pick up the tomatoes on a this greenhouse, So these kind of applications where vision is an integral part of this robot system. Now, the question is, okay, so I talked about the problems, like at least some of the problems, and you can understand that they're very challenging. And they're challenging mainly because of the fact that they are implemented in a real world environment. And as you know, the real world environment is very dynamic, and there are many challenges which are already incorporated there. Okay, so why deep learning? So what are we getting out of this deep learning model for that? Okay, first of all, I mean, from algorithm point of view, the deep learning techniques are some type of neural network model, but in order to ensure good performance, so these models are basically trained on huge volume of data. So now, I mean, if we look into the visual data, so now there are various sources of having this visual data, right? So we have rather cheap cameras, and the mobile devices can take photos. Then, of course, there are zone data, so there are surveillance data and all this thing. So which are essential in giving us huge amount of data on a daily basis. And and given this data and the availability of some uh, kind of automatic annotation tools, and and of course there are many companies and all who are devoted to this annotations of the labeling process. So we have huge volume of visual data, right? Or we can say that visual data, and that is the first requirement of implementing a very good deep learning model. We all at least have the data in the visual domain, so we can train deep learning techniques for this purpose. So this is of course, and one of the major source of this data is surveillance data, and there are many different modes of surveillance, and which capture both static as well as static images as well as videos. And of course, like there are many these satellite images which are available free of cost from many mission. For example, the Sentinel mission from ESA, the European Space Agency, they give this multispectral and radar data free of cost, right? So now this is a huge volume of visual data which are in our disposal, and that actually instigates the research in deep learning for vision. So this is again another point cloud data, as you can see. So each pixel is basically a point having some lat long and depth information. Now, of course, if you see computer vision in general, there are many problems in vision that can be solved using machine learning. Of course, other than that, there are ways to solve the problem using geometry, physics, robot control, and all this stuff, right? And part of the problems, in this intersection, as you can see, they can be solved very well using deep learning. Okay. So now, so that's basically some of the very quick background. Now coming to the recognition problem in general, because I think so that's the main highlight of the work. And if you see the papers in any vision conference nowadays, so majority of the papers are in visual recognition, right? So let us see what kind of problems could be there in recognition. First of all, the first problem is called verification, and which actually says is that within the scene, whether this is a car or not, right? So the output is going to be binary, either yes or no. Then the problem is called classification, where we have to label the image as car because car is present in the scene. The third one is, of course, detection, where given the scene, we need to put a bounding box surrounding that. And so basically, there is some coordinate for the bounding box, which localize the car in the scene. The next one is specific to human, where we just try to find out the pose of the human. So you can say that whether the human is actually standing, he's sitting, all this kind of stuff. The next problem is activity recognition, where we want to know what the person is doing. For example, standing, horse riding, this kind of thing. And then, so these are like all the problems that I mentioned. So they are based on individual object instance in the scene. But now, if we start looking into the whole scene in a holistic manner, the first problem comes is called object categorization, okay, where we want to find out all possible objects which are present in the scene. In some sense, this problem is called multi-label classification because for every scene, as you can visualize here, there could be multiple possible levels. Then, if you go in a fine-grained way, so we want to find out the level for every pixel, and we have the problem known as the semantic segmentation. So that should give you the segmentation map. As you can see here, all the pixels of a given category, so they should group together using a particular color, right? So here the sky is blue, the greenery is green, and all this stuff. Now, so these are the kind of some of the very interesting problem from the visual recognition point of view. Now, what is important in this problem, right? The first important thing is that we need to, for example, here, the algorithm should be able to identify the object and then find some feature from the object so that it can do proper recognition. So the feature extraction is a very important thing. And the second one is, so here I'm giving example from a natural outdoor scene. So the data could be medical data, the data could be indoor data, something like that. So we want our algorithm to look into the data or to explore the property of the data when it extract the feature from the data, right? So this notion of data-driven feature learning is very important. Okay, like how can we explore the properties like the texture, the color, or the geometry of the data to find out the features, right? So this data-driven feature learning property is something which is offered by deep learning. So before the deep learning era, feature extraction was more of an ad hoc method. By ad hoc, what I mean, so there are some certain algorithm so that could give you the feature irrespective of the data, right? So it applies the same set of rules to find the feature. But when it comes to deep learning, then it's data driven, right? So we have a end-to-end system, we can say, and we feed the data, we feed the images, and it's up to the model to find out features from these images, this particular set of images, which are going to be helpful for the task that is solved, right? For example, we are solving classification or we are solving semantic segmentation. The corresponding set of features are directly extracted from the data. So this notion of data-driven feature learning is the key to the success of deep learning, right? So which is not there in the deep learning algorithms. Okay. So, for example, I mean, when we are doing this detection or when we are doing this post estimation, I know that I need to learn a completely different set of features from the image, right? So, I mean, I just cannot use the same ad hoc algorithm for that. And this deep learning model can very well adapt to the different task that you are solving. By the way, here by task, I mean, so detection is a task or post estimation is another task, okay? So based on the task, it can actually extract the required set of features. Fine. So the other kind of application nowadays with deep learning, which is quite popular, is multimodal analysis. Okay, so with multimodality, what I mean is that how can we, for example, incorporate the visual feature with, say, text feature or audio feature. One such example could be image captioning, where we have the image and we want to generate a caption in a like a standard language, right? So for this image, the caption could be a group of people are flying a kite in the beach, right? So this is again a very different type of problem because you have two different, completely different type of data, right? One is a visual data, another is a text data. So how we can align this kind of different modalities is another challenge. But the deep learning techniques are extremely good in handling this multimodality. For example, to encode the image we have CNN, right, the convolution network. Whereas to encode the text, we have RNN, the recurrent network, right? And of course, there are ways to align the two modalities so that finally, given the image, we can automatically output the caption describing the scene. Or another application could be for multimodality is the other way around, where we input the caption and the task is to generate images which are kind of consistent with the caption, right? So as you can see, this problem is very challenging in the sense like in the caption, I just say that a room with a TV and some different type of couch, right? But no other description of the TV or the room or couch is given, right? So it could have different color, different texture. Also, the relative positioning of these objects could be different, right? So the model need to learn very generic concept out of these objects and the relation between the objects so that they can generate a realistic scene. So this is a type of generative modeling in machine learning in general, where I mean, conditioned on some caption, conditioned on some feature, we generate, some visual data and a different kind of visual data. Okay, so this is like conditional image synthesis, as you can say, the problem, and this is extremely challenging, right? So as you can see, so you need to find out the inherent relationship between different objects in the caption. It has to generate a feature based on that, and based on this latent feature, it should produce scene which are realistically looking. So all the scenes are fake in general, right? But I mean, they look as if they are real. Of course, there are some ambiguities which are there, but mostly they look real. Okay, so this is first of all challenging because, of course, this is an image, and for a computer, this is a bunch of numbers, right? So how can we ensure a particular structure or a shape or a texture from these numbers is very difficult, right? Anyway, so that's one problem. So the other problems are basically, okay, by the way, so for this task, there's this generative deep learning, for example, models like VAE, prediction autoencoder, or models like GAN, generative adversarial networks, so which are very popular in solving this kind of task. So I just want to highlight some more problems which was kind of not very much solvable in the pre-deep learning era. But with deep learning, so the feature extractor of the CNN are able to handle some of these ambiguities. For example, the same object can have different poses, right? And still the models are the CNN models are able to extract features which are invariant to this pose. Again, the second is lightning, right? Based on lightning, the identity of the person may change, right? But of course, the deep learning techniques are able to extract features which are this lightning invariant. Then the third one is occlusion. Occlusion is quite common. Like if you have multiple people in a scene, or like there's some object occluded by other. So this may hamper the recognition performance. But again, since deep learning techniques, they extract features in a part basis, like from object parts, and then they aggregate that. So they can handle occlusion to a great extent. The scale invariance, of course, as you can understand here. So since the object in training and test data, they may have different scale. So how to ensure that the features are scale invariant? Then deformation. So the objects that we handle on a daily life are mostly deformable, right? So they're not rigid body object. So how to do recognition with this deformation, right? So as you can see here, there is deformation as well as there is occlusion, there is color changes and all this stuff, right? So this is a very complex recognition scenario. The background also plays a very difficult, important role, and it may hamper the classification performance. So if the background is very cluttered and very complex, the recognition of the foreground object may be affected in that case. So then the intra-class variation, like within the same category, the objects may have very different appearance. So how can we, for example, identify all of this to be a chair, right? Unless we have enough label data in our training set. So the next problem is like if we many of you may be aware of the fact that this algorithms, the deep learning algorithms are based on the notion of sliding window based convolution, right? And the sliding window always looks into a local part of the object, right? But locally, many objects may look similar, right? So how can we take care of this local ambiguity? The next problem is purely subjective. The labels that we usually give, so they might be ambiguous, right? So there is no fixed label usually possible for a given object, right? So now if there are multiple people working together in a company and all, so there may be some ambiguity in the labeling process. And so this is specific to satellite data. So the satellite images may have very different spatial resolution. So the area on the ground that is represented on a single pixel, so that defines the spatial resolution. Okay, and based on that, so here I'm showing some images which are very high resolution to low resolution. Okay, so you can see the whole. You can consider it like if you zoom the Google Earth images. Okay. So, the total like appearance changes, right? And in this case, doing recognition or identification of building or road for example, in the image. So these are quite challenging tasks. Again, in medical data, there is much ambiguity, both subjective manner, again in a visual manner. I was talking about the generative deep learning, the GAN. So nowadays, another problem or rather threat comes up in the form of adversarial attacks, right? So whether the training data that you are using, so are they real data or are the data generated by another deep learning technique? For example, all the images are fake images. So these are generated by a GAN model, okay? But as you can see here, so they are very much realistically looking, okay? So how to ensure that we have a clean training data for a given task? So that's again another problem. Okay. So for all these problems, different deep learning techniques, be it convolution network, be it recurrent network, for detection, for example, this RCNN or YOLO, this kind of models, which are for generative deep learning, the GAN model. So they have come up a long way, and they are popular because of certain facts, right? First of all, we have enough training data, we have good computing resources with GPU, and of course, these are all neural network model, and there are much improvement have been done in the neural network front. Okay, for example, we have very good optimizers nowadays. Okay, and there are the optimizers can adaptively select the learning rate. Okay, and we have ways to normalize the model in different layers. For example, there is layers like batch norm, wet norm, layer norm, all this kind of thing. There is good regularizer. I mean, in these models, for example, you can do a drop out, drop log, drop connect, this kind of, which are basically a layer, right? So, who are used to the traditional machine learning, so you know that to do a regularization, you have to add some extra loss function, right? So either a reach regression kind of thing or lasso kind of thing, right? So which is actually difficult because they have their associated weights. But here, I mean, you can do the same stuff, just incorporating a new layer, right? And these layers are very, I mean, simple, but they are doing extremely good job in finding a very generic feature from the data. Okay. So this generalization capability has increased extensively with this deep learning, and which is like one of the key, I mean, key reason for the success of this model. So just to summarize this thing, I mean, I have been talking about this data-driven feature learning and all this stuff for quite a bit. So the top row talks about a standard method which was followed before the deep learning thing, where basically given the input data, we had to do some feature engineering, like there's some feature extraction algorithm, which we apply without basically considering the property of the data, and the features are then directly fed to a classifier system. But if you see in a deep learning model now, as you can see here, so the feature extraction and the task, the classification classifier, they're actually integrated to each other, right? And that is what we call the end-to-end learning. And for this purpose, the feature extraction is directly governed by the task, the classification task, and accordingly it can extract important and relevant feature from the data. And that is, the deep learning on a single slide. And of course, like you can use this feature that you generate from this thing for different kind of tasks, right? I mean, if you're doing pose estimation or detection or classification, the model can extract that set of feature from the data and do the job, right? So, and that is the main reason behind the success. Now, of course, there are certain resources I've put. So I'll stop here. So the takeaway from this talk could be just to see the and appreciate the variety of problems, the challenges which are there in this deep learning problems, and and of course, it requires some huge amount of data to train the model. And as I'm calling this deep learning, and it's basically neural network with many layers, right? And you may be aware of the fact that in neural network, for every layer, there are many learnable parameters, which are weight and bias. And as the depth of the network grows, the number of parameter also increases exponentially. Okay, so which requires some memory space, okay, some good amount of memory space. Now, given all these challenges, how can we ensure that this model can be put on a mobile device or on an edge device, and then it can do inference? So that is again another challenge from the hardware point of view. So Mr. Tsuchida, after me, so he is going to talk about the difficulties that are there when we implement these algorithms on a hardware. Okay, so I think I'm done, so we can take the questions later, Vishal. So anything else?
So thank you so much, sir. Yes, sir. We'll take the question later on after Mr.
Sure, sure,
Yasuhiro is done.
sure, sure.
Next, our guest speaker is Mr. Yasuhiro Tsuchida. Um,
Okay, thank you so much. Now I'm preparing my presentation. Could you see my screen?
yes, sir. Your screen is visible.
Okay, the rest of my presentation side. As the Professor Biplab mentioned, I'm utilizing the actual the deep learning the technology for social problem solving, and we like to utilize the something with realistic the devices to give the deep learning technology for the actual businesses. It means there is a low cost operation and low cost solution for the customers. To do this, we are very focusing on edge AI solution. I will introduce very detailed later. But so today, I'd like to introduce what is our company, what the services we are offering, and how we can solve something difficulty to utilize the deep learning technology for actual social problem solving with actual devices. Okay. First of all, I'd like to introduce myself. I was spent 4 years Hokkaido University to research AI, the neural network. Although because of less computer resources, it's very difficult to achieve AI application with these technologies. And once I gave up to continue the researching of AI, from 2012 April, I had a chance to work at the US Silicon Valley for new business creation, and I realized potential of AI, deep learning, can be huge business, especially the application for computer vision. So I established AWL company after I came back to Japan. So the name of the AWL is combining AI and bird owl. The owl is considered as god of wisdom in Japanese old myth. We'd like to be the wisdom of our customer by high-level computer vision technologies. So we name as this. Professor Biplab is now the engineering advisor of AWL, and we are collaborating with his laboratory to proceed the researching of advanced machine learning technology, especially the few-shot learning of the domain adaptation to make the machine learning process more efficient, low cost, short term. The very important characteristic of the AWL. AWL is very global company. It may be very general in India, I think, but it's very special in Japan. Almost all the Japanese company is only the Japanese engineers constructing the company, but our company is constructed with the 70 countries, the global AI engineers. We have 3 branches in Japan and Vietnam, and as I mentioned, now we are cooperating with IIT Bombay. The next year, we will establish new R&D subsidiary company in India. We will be focused in India, the important branch to develop machine learning technology. Our developing the technology is Edge AI technology. Our software that will be installed to small edge box called AWL box. The edge box has 2 functionalities. The first functionality is to preserve video data from CCTV cameras, which are installed in actual retail shop. And the second is to analyze the stored video data by deep neural network-based computer vision technology. Thanks to the architecture, it's very easy to install with low cost. The retail shop can be start analysis of the shop easily by this technology. These are lineup of AWL products. The AWL box and AWL box mini, as I mentioned previous page, the Edge AI device to store video data from CCTV camera and to analyze the video data. It can be used to analyze the visitor count, the characteristics of the visitor, or the behavior of the visitors. AWL Lite is Edge AI camera software to be installed on the digital signage device. It will be used for analyzing watching time analysis of digital signage content. Our thermal that will be used in COVID-19 situation as a thermal camera. Okay, from the next page, I'd like to introduce about detail of the AWL box. So this shows the demo images of the AWL box. As I already mentioned, AWL box is used to preserve the captured video image from the CCTV camera like this, And the starting image that will be analyzed by we developed the deep neural network-based application. And this will be used for analyzing the visitor counts or characteristics of the visitors like this. And this video is one of the demo video. In this video, the visitor and the head of the visitor is detected, and these are used for counting visitors and analyzing characteristics of the visitors, for example, age or gender or kind of a thing. That's just a simple application of the visitor count. AWL box that can be used to realize unmanned shop experience. This video shows how AWL box person tracking is very accurate. If a person is hidden by another person, but precisely our technology can track the person. Precise tracking is very important for unmanned shop because if it's mistracking, checkout will be low accuracy. Thanks to the technology, not just unmanned shop experience, it can track a visitor from entering the shop to exit the shop, and all behaviors of the visitor can be analyzed. So that we can generate the visitor much of the information. For example, the entering time of the customer, the exit time of the customer, how long time the customer is staying in the shop, and the age, gender, and the kinds of the something, the characteristic of the customer. And if the customer is revisit customer, in this case, we can put something customer ID for this customer. And the kinds of the dwell time in front of the shelf, what behavior the visitor is taking in front of the shelf, what product the person is taking, and how long time the person should wait in the line of the checkout, the checkout time, or kind of thing. Everything data will be combined as a one tracking the person, and this tracking person, the data will be very effective to analyze the actual the shop situation, and not just this information. For example, the POS data and the kinds of data will be combined to analyze the shop, and this analysis can be utilized for improving store operation and increase the sales. This is the use case to utilize the AWL box. And from the next slide, I'd like to introduce about the AWL's technology. So maybe you are IIT students, and maybe you should have an image that the such technology is very general, just downloading something sample code from the GitHub and preparing strong PP machine, that we can achieve this application easily. But actual implementation for edge device, for example, Raspberry Pi, or the same level something tiny device, is very, very difficult. So now I'm explaining what is edge AI briefly. It's for example, the Google TPU, NVIDIA Jetson, Intel Mobidius, the very tiny deep neural compute chip can be accelerate convolutional neural network inference speed dramatically than CPU inference. Not just inference speed, the chip is very low power consumption and low price. So we can integrate edge AI camera device, which consists of, for example, Raspberry Pi and deep neural computer chip and something web camera. We can realize edge AI camera with very the low cost easily. As I mentioned, the deep neural computer chip is very powerful to construct the edge AI camera. Although deep neural network chip has a difficulty, actually the supported operator is very limited. So it's very difficult to transplant a model which can be working on the NVIDIA GPU machine. Because the several operators should be converted to other operators, which the DNN chip supports. For example, the DNN chip, the GeoFalcon 2801F, is just supporting VGG. It's very high limitation. The models should be converted to the VGG, so it's not realistic to utilize with the modern models. Not just limitation of the operator, but quantization and the model compression is other difficult issue. Almost all DNN chips can work with int8, but general models are constructed with 4.16 or 32. Converting this model into int8 without losing accuracy would be one difficulty. Almost DNN chip has a restricted limitation of the model size. Very tiny model can be working on the chip. For example, the famous detection model, the Yellow B5M, is more than 20 megabyte. But deploying the 20 megabyte model to the chip is not realistic. We need very tiny model. For example, 1 megabyte or 2 megabyte. Although the shrinking of the parameters causes the losing generalization accuracy, it means that the models can be worked on the DNN chip. This will be customized for each installing environment. For example, training the model for entrance of the shop A, test of the shop A, or other the shop B. We need to train the model for each circumstances, each environment. As you know, it takes huge cost for training for each environment, and it's not realistic to utilize it for the actual business. AWL achieved high accuracy and low-cost machine learning operation with utilizing DNN chip by AWL box system we developed. The core module is the AWL Trainer. The AWL Trainer selects suitable raw video for the fine-tuning from the CCT camera environment and send the selected video to the AWL Trainer server. The server side fine-tunes the model with semi-supervised learning technology. So just 1% of the all video data should be annotated to proceed fine-tuning process. The model, train the model that will be deployed to the device, so we can train the model for much of the environment without much cost. Not just utilizing video data of the CCTV camera, we also use the synthesized computer graphics image data. Because in many cases, the CCTV camera video data is very biased. For example, almost all is male or almost all is under 50. To fine-tune the model to all gender, all age, we will add the synthesized data. By utilizing the AWL Trainer, we can reduce time and cost dramatically for fine-tuning process. Customers expecting the edge AI camera solution as a very low-cost solution. Actually, without the AWL Trainer, it's very difficult to offer the services with low cost, but AWL can achieve it. Okay, so as conclusion of the presentation, I'd like to explain about how the engineer is expected for future the HAI engineer. The deep neural network, the computer vision is very interesting technology as future business. The engineering should be commodity, and maybe they're losing the value for the business. But at least the several years, the engineering of the HAI should be the most important factor of the emerging businesses. It means that sophisticating the technical skill to increase the value of the business. Please have the split of the inquiry for the latest deep learning technology. So that you can be the superstar of the business. Okay, thank you so much.
Thank you, Mr. Yasuhiro, sir. That concludes our today's speaker guest lecture. Uh, so participants can ask questions if they have any. They can simply type it on chat. We have two speakers with us who have quite an extensive research experience with them, the domain of computer vision. So if you have any, please feel free to ask them. Simply have to type your question in the chat box. Okay, so we have a question from YouTube. What is AWL trainer? Mr. Yasuhiro, can you please answer that?
Okay, the AWL Trainer is the technology to gather the raw data for the fine tuning and the proceeding actual fine tuning without the manual operation. More details we need.
I think that should be sufficient. It was a question on YouTube.
So actually, why now we are maybe collaborating with the Professor Biplab is Professor Biplab laboratory is proceeding very cutting edge technology of the very cutting edge the machine learning technology like domain adaptation or the kind of the technologies. Professor Biplab, could you explain about what will be the something domain adaptation or kind of the technologies?
Sure. So basically, you know what happens. I mean, when we design these algorithms, so there are certain constraints, right? For example, I assume that I train my model on data which is synthetic, okay, or which is taken from the game environment. And okay, fine, you train your model. And now, I mean, if you want to apply that model or rather test it on data, which is real world data, right? Which are natural objects or natural scene. The question is, will it work or not, right? So in this case, the model will fail because there is some gap or there is some difference in the training and the test data. Okay. Now, to handle this kind of scenario, I mean, what is done? So the idea of transfer learning or domain adaptation is actually used, where we try to align the training and test data, and then on the aligned space we apply the learned classifier. Okay. So that is basically domain adaptation. And as you can understand, so this problem is very prominent because I mean, it's not always possible to get data from the same, to get rather labels for the same kind of data on which we are going to test, right? The data may come from a very different domain. Okay, so now basically to bridge the gap, we have to do some sort of alignment and then we can apply the classifier. So this is basically domain adaptation. And in majority of the applications AWL is currently working on, this problem is very critical because, for example, when you put some model on different locations on different environment, so that I mean we need to adapt the model to that environment, right? And that is why adaptation is quite intrinsic part of these models, and we have been working together, developing this adaptation and how to implement that for real algorithms. Yeah.
Thank you so much.
Okay, we have another question, sir. Can you please elaborate on why implementing DL in edge devices is difficult?
Yeah, Sridhar, you can want to take that question.
So your question is according to difficulty of the implementing on the edge AI, right?
Yes.
Yeah, so actually I already mentioned the edge AI is very powerful solution to utilize deep learning with the technology for the social problem solving, but it has the huge limitation to implement deep learning technique on deep neural network chip. So I already mentioned several points like the quantization and model the size compression, but actually very difficult thing will be to challenge how that we can shrink the size of the model without losing the accuracy. So actually, so for example, I already mentioned Euro B5M is a 20 megabyte, but we should shrink this model to the almost 1 megabyte. It means the 1/20th the compression should be needed. To do this, we should customize the model without losing the accuracy. This will be challenging to implement our model on the edge device. And one more very important feature is the Awl Trainer. So the 1 megabyte the model shouldn't have very generalized accuracy. We should kind of the something overfit to the installing environment. To do this, that we're using the Awl Trainer. So the combination of the customization of the model and Awl Trainer will be very important factor to implement deep neural network with the technology to edge device. Is that answer for you?
Yes, sir, I think that would be sufficient.
Thank you.
Another question which we have received is, I think this will be the last question. How are the deep learning models optimized in edge computing?
Maybe the answer will be very similar as the previous question, but actually to reduce the size of the model will be very difficult, the challenging of the model customization. And the one of the something how to reduce the model the parameters will be, for example, remove the several layers from the original the model, but it causes something the dropping of the accuracy. So this will be how that we can avoid the accuracy the losing to implement the customize the model will be there's something very, very difficult challenges. Maybe I'm sorry. Actually, the answer will be very similar as the previous question, but
Okay. Um, I think we don't have any more questions with us. I think we can conclude this guest lecture now. Thank you so much, Professor Biplab and Mr. Yasuhiro, for coming us and giving us your time. I request the others to maybe leave maybe the WebEx team. Done. Aditya, can you please switch off the live session video and again, thank you, Prof.
Yeah,
Biplab
sure.
sir and Yasuhiro sir, so much for
Thank you.
coming.
Yeah, yeah. Bye.